Good afternoon, everyone, and welcome to the YouTube channel of the International Society for Quantum Gravity. My name is Davide De Biasio, and I'm a member of the Outreach Activity team. Today, I'll have the pleasure of interviewing Professor Don Marolf. Thank you very much for being here.
Thank you, Davide.
That's great. Don Marolf is professor at the University of California, Santa Barbara. He's been working on many different topics within the huge realm of quantum gravity. And in order to kickstart our interview, I would say, would you like to please introduce us to your research interests?
Well, I'm interested in quantum gravity and anything related to it. Einstein taught us a long time ago that gravity has to do with space-time and its structure, and that's a very interesting concept. Our other fundamental theory of physics is quantum mechanics, and anything involving how the two merge is of interest. And the truth is, even things that aren't in that merger. I also am interested in quantum mechanics itself and general relativity itself, classical gravity. But there's a lot of exciting things in the universe that include black holes and cosmology and how things evolve in time. And there's a lot of great things to understand.
Well, this is quite a comprehensive review, so thank you very much. But among all the different things you mentioned, I think that focusing on black holes would be the best choice for today. So if you agree, would you like to tell us something about black holes, still at a classical / general relativistic level? We'll go into the quantum later.
Sure. I mean, Davide, as you say, physics is something that goes in layers of refinement. We don't ever claim to have the absolute answer to anything. We have various approximate descriptions, and it was Einstein's theory of general relativity that introduced the concept of a black hole. And so I can talk about it in that theoretical framework. Again, Einstein's theory of relativity taught us that the structure of space and time is dynamical, and that gravity is in some sense a phenomenon associated with the shape and curvature of space-time. And not only that, space-time becomes a physical, well, as I said, it's a dynamical thing. It can wiggle and produce gravitational and support gravitational radiation. It can carry energy, and the wiggles of space-time themselves can gravitate and cause additional curvature. So a black hole is a phenomenon that is associated with certain kinds of space-time curvature that is strong in a certain sense. It produces a very strong gravitational field, and it has the property that it's a sort of finite-sized surface in space-time. Really, a black hole is best described in terms of what we call its horizon. And the horizon is a finite-sized surface in space-time where information inside, classically, can't escape. And the reason it can't escape is because in relativity, information can travel only at less than the speed of light. And in some sense, the escape velocity of this region has become greater than the speed of light. And so all information is therefore trapped. And we call it black because light itself is trapped. If there happens to be a star shining inside the black hole, the light, again, can't move outward, can't pass the escape horizon. And so we don't see that light. And so it looks black. Stuff falls in and doesn't come out. And actually, that's the most important property of a black hole that will come up again later in our quantum discussions, is that at the classical level, what a black hole is a region of space-time where things can enter but not escape.
Well, picking up from where you left, you mentioned the word information, right? Which appears to be extremely important in describing what black holes are and what the properties of black holes are, and we'll come back later. So before moving on, may I please ask you to expand on this word? Like, since it's a word that also appears in natural language and, everyday life, may you please tell us what physicists mean when they say information?
Well, let's stick at the moment at the classical level, because again, there are various levels of approximation. What I mean particularly is if there is some thing, perhaps a person inside the black hole, that no matter what they do, there is no way for them to transmit a signal, intentionally or otherwise, to anyone on the outside. And so information is something that you would attempt to send, and it could be anything. It could be, it would be something that Okay, again, at the level of approximation where we pretend that humans have free will, then anything that you decide to send, the question is, can I get it?
Okay. I think this is quite clear. So black holes, in a sense, are particular configurations of space-time. They better be thought in that way instead of objects that have this property of not allowing information to get out. Now, you said at the very beginning, and that's the whole point of this YouTube channel and this society, right, quantum gravity, that general relativity, which is the theory that gives us the picture you outlined before, and quantum mechanics need to be merged, right? What do you mean by this? Namely, why do we need to do this? And then we'll go back to black holes, clearly.
Well, why do we need to do this is a question that can be answered again at several levels. From a just theoretical point of view, the issue is that our understanding of physics is clearly incomplete. On the one hand, we have this understanding that Einstein taught us about general relativity and the curvature of space-time. On the other, we have an understanding that physics is fundamentally not the way that Newton taught us, and it involves this strange thing called quantum mechanics. And we know that everything else in the universe is quantum mechanical, and we know that it's very difficult to have a quantum mechanical system like electrons and photons and things that can interact with a truly classical system. So that suggests that gravity itself must also have a quantum mechanical aspect. And we could go on a long discussion of that, but I don't think that's the primary focus of this interview. And then it turns out that if you try to apply the standard rules of quantum mechanics to Einstein's theory of relativity as it's written, there are various confusing things that happen. And they're sometimes called problems or paradoxes, and that will presumably need to be, well, they're things that remain to be understood, I think is the right answer. And what people usually mean when they say merging those two theories is to develop a complete understanding of those phenomena. The one which was talked about for years and years and years is the so-called non-renormalizability of perturbative gravity. That's a bunch of technical words, but fleshing them out would take us again rather far afield. I think the one that you're probably more interested in today has to do with black holes, and it was something that came up in Stephen Hawking's work in the 1970s, and it's generally known as the information problem.
Yes, clearly you anticipated where I was about to go, right? Because my follow-up question would have been, may you please tell us something about the ways in which this necessity of merging general relativity and quantum mechanics affects our understanding of black holes? So feel free to start where you like. I mean, you already mentioned the information paradox, but you can take it.
So the interesting thing is that the first thing that Hawking did in the 1970s has actually nothing to do with merging the two. It's all about how quantum mechanical things like photons behave when they're interacting with a black hole that for the moment we'll try to keep classical. And as I say, when a quantum system and a classical system truly interact, well, there's problems. It just doesn't work very well. But you can, if you treat the black hole as what physicists call a fixed background, a kind of a stage that is not altered by the play that takes place upon it, then you can study photons in this environment created by a black hole. The point is that we're going to pretend for the moment that no matter what happens, the black hole never changes. So it's not really interacting with the photons. We're just going to see what photons do when they're near a black hole. And what Hawking discovered using the principles of quantum field theory that have really been well tested in many other experimental situations over the last 100 years, what he discovered is that if you have photons near a black hole, or if you have I should really say, if there exists an electromagnetic field in the universe and the universe contains a black hole, then what the black hole does is to sort of tear apart the electromagnetic vacuum in such a way that it will constantly send photons outward to infinity. And it will also in some sense, absorb things that are sometimes described as virtual photons or sometimes called Hawking partner photons. But there's a little bit of weird stuff here because it turns out that you can think of this tearing apart of the vacuum as happening right at the event horizon that we mentioned before, the boundary that information can't pass out of. And if this side is the outside and this is the inside, then the so-called Hawking particles move outward from the horizon. But the so-called partner particles, or sometimes they're briefly described as virtual particles, but things, they move inside this way, in a certain sense. And the interesting thing is that this tearing apart of the vacuum can produce these two particles and still satisfy conservation of energy, because it turns out that inside the black hole, objects can have negative energies if they move in a certain direction. It's another thing we could talk about more. It's a property of the classical black holes, but it's a true thing. And it is what enables this so-called pair production of Hawking particles, because there's a positive energy particle that streams outward and a negative energy particle that is in some sense entering the black hole.
So first, I'd like to thank you for this overview, but I have like 3 questions starting from the very beginning of your discussion. When you say, which might be helpful for our audience, like when you say that we take the black hole as a fixed background, you mean that we already introduced some kind of approximation in our discussion, right? We neglect the fact that the presence of particles and electromagnetic fields carrying energy and so on and so forth might alter the shape of our space-time, like the geometry of our space-time. Is this correct?
That is correct. That is correct. We pretend, so we forget some of the things that Einstein has taught us intentionally in order to make a system that is at least mathematically consistent. However, we believe it's a consistent approximation, as you say. In fact, people may recall that in high school physics, they probably learned about Newton's constant of gravitation, big G, which controls the strength of gravity. And there's a sense in what we are doing, and G is famously some tiny number. In SI units, it's of order 10 to the minus 27, if I remember correctly, or someone will correct me if I'm wrong, but it's very, very small.
I'm not the right person to ask because I'm really bad.
We can Google it quickly.
Yes.
but 10 to the minus 27 is a tiny, tiny number, and we are for the moment approximating that by 0.
Okay.
Which is not a bad approximation for many things, especially if you're worried about the possible effect on the black hole of, let's say, 1 photon. Okay, so yeah, we're going to talk about 1 photon at a time. And in principle, that photon produces some additional gravitational field. It changes the gravity near the black hole. It changes the shape of space-time, because Einstein taught us that all energy does that. But for the moment, we're going to ignore that effect and pretend that well, it's just, we expect it's true that 1 photon doesn't change things very much. And to get a system we can study and analyze, and to find something which is mathematically consistent, we're going to just set Newton's constant to actually 0 and ignore it completely.
So if I understand correctly, you're saying that gravity is so much weaker when compared to all the other things that happen in the universe, like controlled by a very small constant and so on and so forth, that in some sense we can neglect it and expect our description to still kind of properly apply to the setting we are discussing, right?
Well, in this case, it's not really, I mean, there is a sense in which gravity is a much weaker interaction than electromagnetism or the strong nuclear force or some such thing, but that's actually not the point here.
Okay.
The point here is that we want to talk about something, we want to talk about a black hole, and that, as your listeners may know, the black holes we found in our universe tend to be rather large, at least 5 times the mass of our sun, maybe 50 times, maybe 1,000,000 times, maybe 1,000,000,000 times the mass of our sun. And these are large things on microscopic scales. And the question is really, if we're talking about a photon, and now I haven't told you what energy we're talking about for the photons yet, but I'll get to that very, very shortly. It turns out that it's natural to characterize photons produced by this effect that Hawking described in terms of a temperature. And it turns out that we're going to be interested in photons that are sort of thermal with a temperature of microkelvin. And microkelvin photons, don't produce much gravitational force. we've got, I'm sitting here in a room where, okay, I'm in the US, so it's 70 degrees Fahrenheit, but there's thermal photons all around that have temperatures much higher than microkelvin, and I don't feel them pulling on me. And if I was a 5 solar mass black hole, I would feel the effect even less. And so that's why it's okay to neglect this gravitational effect of 1 millikelvin photon, or sorry, microkelvin photon at a time pulling on a black hole.
Thank you very much. Now, so in a sense, the gravitational effects induced by the presence of these photons are so much smaller than the whole thing happening with the black hole that they are kind of negligible. Okay, so moving to my second question, being a bit practical for everyone listening to us, when you say that these particles are produced, you mean that someone like sitting very far away from the black hole with some kind of particle detector, like some kind of, those normally used in experiments, would see particles arriving from the black hole. Is this more or less the kind of picture you have in mind?
That's correct. That's correct. So again, there's some effect that in some sense does something to the vacuum and sends something outward that carries energy, and it turns out that it has the characteristics far away that we usually call a particle. And so yeah, if you sit outside the black hole with a particle detector, your eyes aren't quite good enough to see microkelvin photons, but something that would detect them, then every once in a while, your detector will register a photon going by, which in particular indicates that something is carrying energy away from the black hole. And that process of energy leaking out is, as we said, compensated by what is in some sense described as negative energy flowing into the black hole, which therefore must reduce the overall energy in the black hole. And we expect that if the process continues for a very long time, the total energy in the black hole becomes very small. And Einstein's theory does tell us that when a black hole has small energy, it also becomes physically small and shrinks to zero size. And so we expect that the black hole gradually, well, if the black hole were isolated by itself in the universe, if it wasn't in our actual universe, the cosmic microwave background left over from the Big Bang is 3 degrees Kelvin, which is much hotter than microkelvin. And so the black hole actually gains energy from the cosmic microwave background faster than it can radiate. But if we didn't have that, if we really be theorists for a moment and put the black hole in an isolated universe, then we imagine the black hole would slowly shrink by radiating these Hawking photons. And that process is called black hole evaporation.
And we'll get there. But before that, let me jump into your explanation when you said that this energy being carried away needs to be compensated. You're clearly referring to the fact that energy is conserved. I just want to stress this. So if you get energy from the black hole, whatever happens, needs to lose energy. And in order for that to happen, you mentioned this idea of particle carrying negative energy within the black hole. Can you please tell us something about this idea, this concept, which might appear quite confusing to first time?
It is confusing to the uninitiated, because negative energies are things that don't usually appear in physics, and we don't like them. One reason we don't like them is that when they do appear, they usually they mean that the energy isn't really, usually it just means the energy is less than you thought it was, and it may not be truly negative in some sense. But things inside a black hole, and also if we want, as most students of physics know, if energies could become arbitrarily negative, it would tend to destabilize systems, because systems like to sit at their lowest level of energy, because that produces lots of entropy, and the second law of thermodynamics pushes things in that direction. So if you go to arbitrarily negative energy, then things would tend to be unstable. They wouldn't have a ground state that would hold them. And that's actually part of the issue with the black hole, that it turns out it does have these negative energy degrees of freedom inside. And I can say a few words that might make people a little more comfortable with that. So the theory of general relativity is an interesting theory. It tells us that, again, space and time can have shapes, if you will, that we're not familiar with. And it tells us that space and time go together as one thing called space-time, and that the two are related. So It turns out that okay, I'm torn between my desire to make this sound accessible by cheating and my desire to say things that are actually true.
You can try to say things that are actually true. I'll jump.
I will try to say things that are actually true.
As far as we can concern when black holes and their evaporation is concerned, clearly.
Yeah. So I guess I'll say this. Just like relativity teaches us that space and time are part of the same entity, they're two aspects of the same thing. It also teaches us that energy and momentum are two aspects of the same thing. If people have studied special relativity, they will have seen the concept of an energy momentum 4 vector. I don't know where that comes up in various physics curricula at this point, but it's a true thing, and the relationship between energy and momentum is very much like the relationship between space and time. And because space and time get kind of screwed up inside a black hole, or at least they take a very non-standard shape, something we're not familiar with, okay? And therefore, the space and time inside a black hole have unfamiliar properties. It turns out that energy and momentum inside a black hole also get kind of mixed together in a way that is unfamiliar from standard Newtonian physics, or even from special relativity. And as a result, the thing that actually is the conserved quantity we call energy is if you study that notion of energy for things inside a black hole, it's actually more like what you're used to thinking of for momentum. And as a result, it turns out that if you're inside a black hole, there's a sense in which if you're moving in one direction, you have positive energy, but if you're moving in the other direction, you have negative energy. It's just in the same way that we would normally assign this property to momentum. The momentum is positive in one direction and negative in the other direction. But again, energy and momentum get kind of meshed and melded together inside a black hole so that now energy has this property. And so while there are many things inside a black hole with positive energy, there are also things inside a black hole with negative energy. There can be.
So in a sense, since energy and momentum in a advanced context like special or general relativity are part of the same spatiotemporal object, and space and time get kind of mixed inside the black hole, energy and momentum get mixed too and behave in weird ways. Can this be a good summary?
That is correct. That is correct. And I feel like I should add one more element of truth for your listeners, because if they're paying attention, they may have been confused by something I just said. So it really is true that this notion of positive versus negative energy inside a black hole has to do with what is, in some sense, the direction the object is traveling. And objects that actually fall in from the outside and travel towards the inside, as most things tend to do, have positive energy. So the confusing thing is that I mentioned these Hawking partner particles having negative energy. Well, to be consistent, they then have to be traveling outward in some sense. And that's kind of true. They are trying to get out. However, we agreed, but there are still physical excitations that travel at less than the speed of light. So since even things that travel at the speed of light can't escape from the black hole, they don't get out. And even though they are in some sense trying to get outward, it turns out the whole thing is sort of falling inward, and there's a sense in which they separate from the horizon nonetheless. And as a result, there is, even though they are moving in the outward direction, okay, they have an outward directed velocity, if you will, it is still true that they carry this negative flux of energy inward into the black hole. So I wanted to admit that confusion, and I don't know if that actually clarifies things, but at least people will know that they're confused for good reasons, as opposed to me just making mistakes.
In a sense, black holes can be thought, if you agree, as cosmic tapirulans, right, in which you try to run away and get pulled in because you cannot run faster than the speed of light when you are at the horizon, right? And before getting back to our black holes, at the very beginning, you mentioned the electromagnetic field and photons, right? But just to make it clear,
Yeah,
that was just an example, right? Whatever particles you have in a universe, those will be radiated by a black hole. Is this correct?
that's right. That is correct.
Perfect. So you have these negative energy particles that,
Well,
as you
I
said,
should sorry, I should clarify one thing, which is that in principle, the black hole radiates whatever particles you have. But as I said, the radiation is characterized by a temperature, which for solar mass scale black holes is kind of microkelvin. I think it's microkelvin. Maybe it's millikelvin. I always forget. But anyway, very less than a Kelvin. And the point is that a particle with a lot of mass uh, doesn't typically appear in thermal radiation at that temperature. And as a result, in practice, black holes don't radiate massive particles, they only radiate massless particles. But in principle, there is a tiny rate at which they also radiate electrons, protons, houses, suns, and all kinds of things like that. But I mean, that's a tiny rate. That's, it would take more than the lifetime of the universe to produce some of those things.
yes, that's a matter of probabilities. So in a sense, you have this black hole, and as you said, it appears to be shrinking, right? Because we collect radiation from far away, it loses energy, it has to, because energy is conserved, and it appears to be shrinking. So a natural question would be, what happens while the black hole shrinks? Does it stop radiating? Does it radiate more, right? And what happens for longer radiation times?
Yeah, it's a natural question. And as we said, all we really use to derive this are two things. One, the idea that for each photon being produced, we can neglect the gravitational field carried by the photon. So we can ignore the details of how that photon produces or alters gravity. But that we assume that somehow energy is also still conserved. And therefore, when we see this negative flux of energy into the black hole's energy should go down. And then we use Einstein's theory of general relativity to tell us that the black hole shrinks. And so you can ask the question, how long should that go on? Well, I've argued that those are reasonable approximation for solar mass sized black holes. Okay. And so as long as the black hole is, so maybe it starts out at 5 solar masses. If it shrinks to 1 solar mass, those still sound like pretty good approximations. If it shrinks to 1/10 of a solar mass, still sounds like pretty good approximations. Okay. And in fact, you can analyze this more quantitatively. And the place where a sort of naive analysis would say that the effect of a single photon's gravitational field in a black hole becomes large is when the black hole shrinks to be what's called the Planck scale, which is 10 to the minus 35 meters. Is that right?
Yeah, yeah.
Okay.
I think that's right. Yes.
Very tiny. Oh, sorry. I was in mass units and I switched to length units. So this solar mass black hole is about 3 kilometers across.
Yes.
So 3 times 10 to the 6th meters. And the place where you'd expect the approximation to break down is when the black hole becomes 10 to the minus 35 meters. Okay.
Mm-hmm.
Maybe I'm wrong about that. Maybe there's an effect that's a billion times larger than I said, and the approximation only breaks down when the black hole shrinks to 10 to the minus 26 meters. But that's still really tiny. Okay. And when the black hole gets to be that small, well, anything could happen. That gets into the regime which is obviously described, which is naturally described by the details of how gravity and quantum mechanics work. And there could be all kinds of corrections to general relativity. And, who knows what happens. But what's interesting for our discussion is that if the black hole starts out at 5 solar masses, by the time it gets to 3 solar masses or 2 solar masses or a half solar mass, not much seems to have changed. And so presumably the radiation process continues at least past that level. And that's where this thing called the information problem arises.
Yes, and this is natural follow-up question, right? Because if you claim this approximation to be adequate even for very small black holes, where is the paradox? And in particular, where does information appear in this whole discussion? Because it seems not to have appeared, except for the fact that information cannot escape black holes, but that is a solid fact in general relativity. So why information? And more importantly, why paradox?
Well, I have to admit, I've never liked the word paradox.
Me
That seems a
neither.
little that seems a little bit heavy on the advertising. I like interesting
Yes.
problem because it's an interesting question, okay? And it is a problem from certain points of view that it's a thing that we would like to understand better. Okay.
Or the information approximation failure, or open question, or as you
Problem is fine.
like to
Problem
put.
is fine.
Yes.
All right. But let's talk about what that is. And to describe the information problem correctly and why it is such a problem, because as you say, eventually we know there's going to be new physics that comes in. We don't pretend to understand everything about the universe. And eventually things will happen to change this Hawking process and well, whatever. Okay. But why is there a problem? So this has to do with the subject of gravitational thermodynamics. And this is another interesting thing we've learned from, well, both from classical general relativity and also from this work of Stephen Hawking involving the Hawking radiation I just described. One of the interesting things about the Hawking radiation is that it really is characterized by a temperature. It's very thermal, which tells us that black holes in some sense have a temperature. Okay. And I want to make that very physical. Because the radiation produced by a black hole is thermal, if you had some other thing that you know and love that you say has a temperature, like a star, okay, and okay, a star is not very good because it's actually more like 6,000 Kelvin or something. But if you had an object, well, okay, let's take a star. If I had a black hole, so solar mass black holes turn out to have microkelvin temperatures, but smaller black holes, Hawking tells us, have larger temperatures. So I could imagine in my theorist universe that I had a black hole whose temperature was 6,000 Kelvin. It turns out, if you work out the numbers, it's still in the regime where you'd expect all these approximations we discussed to apply, and that one photon is still a negligible effect on the gravitational field. So because the black hole produces this perfectly thermal radiation.
Pardon me if I jump in. It is important to remark that smaller black holes appear to have a larger temperature, right, than big black holes. This is very important and maybe counterintuitive, but that's a thing, right?
That is a thing. That is correct. It is very important, as you say, maybe counterintuitive. Although it fits with the following idea, which may increase your intuition, which is that, as I said, the effect is due to the black hole horizon doing something to the electromagnetic field. And in fact, the relationship between a black hole's size and its temperature is very simple. It turns out that a black hole of this size tends to produce photons with this wavelength. The size or wavelength of the photon is about the size of the black hole, which that may or may not be obvious, but it's not a ridiculous answer. And in particular, if I put a trained physicist in a closed room, and even if they don't know anything about these theories involved, if I just tell them to make some blind guess based on sizes of things, what's the effect of an object this size, they might use this thing called dimensional analysis and come up with the idea the photon was the same wavelength. The wavelength of the photon is the size of the black hole horizon. And that turns out to be what Hawking's calculation says. So it's really because the black hole is an object that causes a disturbance of this size in the electromagnetic field that the Hawking effect happens.
Thank you. I think this makes it quite clear. The only thing is that we are not used to things that evaporate and get hotter while evaporating, right? So things
exactly
get colder, right? But I didn't want to really spoil the end of this. So if you want to get back to the star and the small black hole, this was just an important remark.
Yeah. So if you have a star, a normal star, and if you have a black hole of the same temperature, and if you put them in a closed box, they will happily exchange energy and remain in thermal equilibrium. I say happily, it's not quite true because of this problem you mentioned that if the black hole happens due to some random process to absorb a couple of extra photons from the star, then the black hole grows and gets bigger and then gets cooler. And now, on average, it does absorb more energy from the star than it radiates. And so the equilibrium you would make between a black hole and a star is thermodynamically unstable, we say. But nevertheless, for long periods of time, there can be such an equilibrium. And in this way, the black hole really does behave like it has a temperature. So where was I? Oh, I was going to talk about black hole thermodynamics. That's right. So one of the interesting things that we learned from actually Einstein's theory of relativity is that black holes satisfy something called the laws of black hole mechanics, which in pure general relativity, they appear to be analogs of the laws of thermodynamics, including the second law, which says that the entropy increases. And the analog of that in the black hole context is that the surface area of the black hole increases. And the really nice thing is that when you combine this with Hawking's observation of the black hole temperature, you can translate those laws of black hole mechanics into a form where they look just like the laws of thermodynamics. And therefore, they seem to tell us that black holes really do have an entropy, like any thermal system, and that the entropy of a black hole is given by the area of the event horizon as measured in so-called Planck units. So again, the Planck length is this scale, which is roughly 10 to the minus 35 centimeters. So you imagine a square, 10 to the minus 35, sorry, 10 to the minus 35 meters. You imagine a square, 10 to the minus 35 meters by 10 to the minus 35 meters. So it's 10 to the minus 70 square meters. And you cover the surface of a 3-kilometer sphere with those things for a solar mass scale black hole. And then you can count up how many dots you've got, and that tells you the black hole's entropy, which is absolutely enormous. Okay, so black holes have an entropy which is enormous, but finite.
They have a temperature, they have an entropy, and they follow laws which resemble in quite a striking way the laws of thermodynamics, right? This is kind of the summary of what you said.
That's right. That's right. And they seem to really have an entropy in the sense that, and as you say, the laws are derived formally in a way which you might say they're analogs of thermodynamic laws. But if you perform typical thought experiments involving Carnot cycles or exchanging radiation with a black hole or dropping in ideal gases to a black hole and trying to get energy back out, this entropy-like quantity for a black hole called the Bekenstein-Hawking entropy behaves like an entropy thermodynamically. So what can I say? All right.
People usually say that when something quacks like a duck, looks like a duck, walks like a duck, maybe not 100%, but probably it is a duck, right?
Oh, there you go. There you go. That's right. So the interesting thing is that a modern understanding of entropy is based on statistical mechanics, which is a fancy word that says that entropy counts the number of configurations or the number of states, as physicists say, that an object could have. So if you tell me that a box of gas has a certain entropy at a certain temperature, that means that there are only so many distinct ways in which its atoms can be arranged. And because of quantum mechanics, it's really a finite number. It's not just, there's not really a continuum of things there. Quantum mechanics tells us that these things are really finite. So it seems natural to believe that black holes also have a finite number of internal configurations given by the Bekenstein-Hawking entropy. Seems natural to believe this.
Okay. And kind of assuming this, right? Starting from here, which is quite a safe assumption, I would say, given all the arguments we brought, where does the information problem appear within this context of black hole thermodynamics?
So here's the problem appears. We talked about this process where you start with a large black hole and you produce Hawking radiation. And for each Hawking photon that goes out, you produce another so-called Hawking partner photon on the inside of the black hole. And let me choose a case which is perhaps, this is a special case, but, well, okay, let's just talk about photons. It turns out for photons, I can say this in a language which is not actually the strongest argument, but which is more easy to see. So for a photon, if I produce this Hawking partner photon, well, photons can have different polarizations. They can have a vertical polarization or horizontal polarization, or they can have, you could think of circular polarizations, left circular and right circular. So we produce this photon. What's its polarization? Well, it could be left circularly polarized, or it could be right circularly polarized. And Hawking tells us that because these things are produced thermally, half of them are left circularly polarized and half are right circularly polarized. But he also tells us that this thermal production of photons is, using a word you mentioned before, probabilistic. And so which photon is left and which one is right circularly polarized? Is the one produced at noon on Thursday left circularly polarized, and the one produced at 2 o'clock Friday right circularly polarized, or is it the other way around? So for each Hawking partner that goes into the black hole, it could be either left or right circularly polarized, which seems to give us two configurations inside the black hole. Okay, fine, two configurations. Now, these particles aren't produced very quickly. I mentioned that the particles have a wavelength which is about the size of a black hole. They're also produced on a time scale equal to the time it takes light to cross the black hole, which is, light's pretty fast, but it's not infinitely fast. So these things leak out one at a time. And they accumulate inside. So the first photon can be either left or right circularly polarized. That gives us two configurations. But then we have another photon that comes another Hawking partner photon produced sometime later, which also has two possible polarizations. So now there's 2 times 2, which is 4. Okay, fine. But then the third one will have 2 as well. So it's 2 times 2 times 2, which is 8. And so the number of configurations increases exponentially as time passes. Now, it turns out entropy is usually defined as the logarithm of the number of internal states. So that means that there's some entropic-like number. There's an entropy inside the black hole, which is increasing linearly with time. Okay, fine. But if you sort of count up all the entropy produced in this Hawking radiation rate, it turns out the entropy that would be associated with the Hawking partners inside the black hole is actually about the same as the amount by which this Bekenstein-Hawking entropy of the black hole, the surface area in Planck units, shrinks. So let me just try to make this pictorial for everyone listening. What's happening is you've got the entropy of the Hawking partners apparently going up like this inside the black hole, whereas the entropy of the Bekenstein-Hawking entropy of the black hole, which Davide was kind enough a minute ago to agree that it was a very reasonable conjecture that we should assume that it measures the total number of possible configurations inside the black hole. That starts up here at some large number and goes down like this. And what I just claimed without calculation, but because everything is basically here following from dimensional analysis, it turns out to be true, is that the slopes of these curves are basically the same. This one goes up at basically the same rate as this one goes down. So at some point, they clearly cross. And when they cross, which is about the time when half the mass of the black hole has disappeared, so when our black hole shrinks from 5 solar masses to 2.5, when they cross, we appear to have this problem that the Bekenstein-Hawking entropy, which appears to be the maximum number of configurations that are possible inside a black hole, is less than the actual number of configurations that Hawking predicts for the partners inside. That's the evaporation problem. And it's a problem because if this conjecture about the Beckington-Hawking entropy being the number of internal configurations is true. It's happening when the black hole is still really, really large, and all these approximations seem incredibly natural. Okay, so that's the problem.
Yes. So just to sum it up, because we have an approximation that, as you said, appears to hold as long as black holes are large and not like super, super, super tiny. We have these black holes that evaporate. We have this entropy coming from these Hawking particles getting in. And at a certain point along the evaporation of the black hole, we have that the entropy carried or realized or due to the presence of these Hawking modes goes above, like it's bigger than the actual entropy of the black hole, the maximal entropy of the black hole as given by Bekenstein's formula. And this implies that we should have more entropy than in the maximum value of entropy allowed, which is clearly some kind of contradiction. And I just want to remark that that happens when the black holes are still quite large. So it appears that we have a problem which calls for a solution. Do you agree on this? Like, is this
Absolutely.
summary apt? Okay, so as people might imagine here, there's a lot of possible solutions to this which have been proposed and so on and so forth. But I would like to ask you something about one of these, which is the firewall proposal. Do you want to tell us something? If you would agree in framing this as a solution to the information problem, like, would you like to tell us something about this?
I'm not really sure that I'd frame it as a solution. Uh, Let me describe it in these terms. So at some point, um, a few years ago, collaborating with Joe Polchinski and James Sully and Ahmed Al-Harry, we pointed out just various thought experiments that you could use to probe various solutions people had mentioned in the past. And the idea of any thought experiment is, I mean, let's admit that this is all very theoretical. We don't have black holes in our laboratories. We have detected their existence in various ways in astronomy, but we don't have them in our laboratory. We've never directly measured Hawking radiation. You know, there's a lot of things going on here. You'd be forgiven for thinking this is all angels dancing on the head of a pin, et cetera. But it has produced a lot of interesting research and it remains a lot of interesting questions. All right. In any case, we were trying to produce more thought experiments to probe ideas that people had suggested for resolving this problem. And the idea of any good thought experiment, since it's again just a thought experiment, it's not a real experiment, is to produce some kind of reductio ad absurdum, something which is just as ridiculous as it could be. And what we showed was that various ideas people had in the past had various internal inconsistencies. They didn't actually work even on their own terms. And then the question is, what might appear to replace that? And so we put forward what I would call a sort of straw man proposal. It wasn't obviously, correct, but it's the most naive thing you could think of, which is that, let's see, how do I say this? I described Hawking's calculation as something that happens where the black hole horizon tears apart the vacuum of the electromagnetic field to produce these particles. And so if you need some effect to kick in that makes the evaporation stop before this problem occurs, the most obvious thing is for the electromagnetic field no longer to be in its vacuum state near the black hole horizon, because then there's not a vacuum to tear apart and the Hawking calculation doesn't go through. And so basically that's what we said, is that if physics is going to be consistent and if Hawking radiation either stops or continues in some way after this problem arises that resolves the problem, that brings the actual entry inside back down, that there can't be a vacuum-like state near the black hole horizon. It has to be very non-vacuum-like, and therefore it has to be something you could think of as very hot. And we, kind of pictorially, as I said, for a strong man, described it as something like a wall fire, if you will, a very hot region around the black hole that would burn up anything that tried to fall in. So that was where the name came from. I'm not sure that truly pictorial idea should be taken particularly seriously because, first of all, there certainly was no coherent theory behind it. Okay? It was not something derived from some more consistent story. It was just, one seat of your pants way out of the problem.
Okay.
What I will mention though is that what I think we have, I think a spirit of that carries through, and that I would defend as a likely scenario, is that whatever's going on after this problem arises inside the black hole is very, very different from normal physics as we understand it. And I think there is a sign that something fundamentally changes, and we could have a longer discussion, maybe a couple of more interviews would take a couple hours to get there. But I think many of the more recent developments point to the idea that the space and time inside a black hole, which is old enough to have this problem, okay, and I emphasize that the black holes in our current universe aren't even going in that direction. They're actually getting bigger instead of smaller because stuff is falling into them. But if you had a black hole that was isolated and it radiated and was old enough to have this problem, then a lot of our current results indicate that space and time inside the black hole just wouldn't exist in anything like a form that even Einstein's theory of relativity would predict. And what that means, I don't know, but I'd sure like to find out.
Thank you. Thank you very much. So I think this is a good point to just ask you whether you mean that in order to kind of have a grasp on what might happen inside of a black hole at that point along the evaporation, since you say that space and time are wildly different from anything we can think of, we would really need not only a solution within our framework, but really some theory that goes beyond general relativity. Is that what you mean? Like, is this something that's like, yes, okay. Like, so this is the famous quantum gravity people have been talking about, right?
Yeah, so what's really interesting is that this seems to be a very sharp sign that something we call quantum gravity really is relevant in a sharp and important way, even for objects that are still fairly big, like objects that are 2.5 solar masses, for example. And that is still a surprise, but it appears to be an inescapable conclusion.
Well, and from this point, first of all, thank you. Thank you for all your nice explanations. If you allow me, I would like to move from these more physical discussions to a rather more personal question before closing an interview. Namely, I would like to ask you, because I think this can be very important for all the students trying to find a way and listening to us, why you chose to work on these topics. Like, what led you into black holes, quantum gravity, the information problem, and so on?
Desire to understand how the universe works. And there are many ways to explore that, of course. I mean, all of our friends across all of science explore that from all kinds of different directions. I guess, well, you go into this field because you're a real gambler. This is the ultimate long shot. It's a place where we feel like we're seeing some clues that may teach us about really fundamental things in our universe, things that go beyond quantum mechanics and general relativity and our understanding of space and time. Of course, it's a long shot because there's only a few clues, and we don't have we can't test them experimentally in the laboratory. So there you go. But it's an attractive issue. And although we haven't really had a chance to discuss it here, I do feel like we've been making some real progress on this recently, perhaps for the first time in the almost 50 years since the problem came up. So it's an exciting time to be in this field, and I plan to continue with it.
Well, I guess that this is absolutely an interesting answer. And I think this might be the topic for a follow-up discussion, if you agree. But for the time being, I want to once more thank you for being here and thank all the people that have listened to us. And I hope to see you someday.
Sounds great. Thank you, Davide.
Thank you and goodbye.
Goodbye.